Thanks for attending my talk. This is Fast Inference Furious Scaling. My name is Rafael. Does anyone know the reference of that title? You know the movie? Okay, good. I'm a bit proud of that title. It's not AI generated, but probably more proud than I should be. But yeah, that title is not just about vLLM and KServe, which I'll talk about later in this talk, but it's I think it's trying to capture, I guess, like the space of LLMs in general, especially for beginners who I kind of made this talk with in mind. There's kind of a space that has new tools, new techniques, new announcements, new AI-generated LinkedIn posts every day. So it could be overwhelming for them who want to just kind of get started in the space. They want to learn about the space, and maybe they want to contribute to some of these projects as well. So you might have heard of vLLM or KServe, but maybe you don't really know what exactly they do or where they fit in. So I'll give a background on why serving LLMs is challenging in the first place, and then from there show how vLLM and KServe are actually trying to solve those problems and fit into the landscape. Then hopefully, if I have time, I'll show a bit of a demo where I get KServe and vLLM working together on my laptop. So I'm Rafael, as I said before. I'm a software developer. I'm from Toronto, Canada. We don't have as many bike lanes as Amsterdam, and I wish we did. But I work in the open tech team at IBM. I've been there for on this team for about 3 years. And besides contributing to open source, I present workshops and talks like these, and I really enjoy mentoring new contributors who want to get involved. I also previously maintained a project called Model Mesh, which is a component of that KServe platform. And more recently, I began to contribute to vLLM, which is, again, sort of the inspiration for this talk, because I delved more into the inference side of things and saw how overwhelming it can be when you have no background in it. So to start, let's talk about why it's hard to serve LLMs in the first place. So first, what does it actually mean to serve a model? Very simply, serving a model is just making it available for users to actually consume and receive responses from. When we use cloud-based services like a ChatGPT or a Gemini or a Grok or something that's easy to sign up for, those models are being served to you, and they're for you to consume, and usually that's via some kind of API endpoint. But of course, it's not that simple. A lot happens behind the scenes. Your prompt is getting broken down into tokens. That model is processing all of those tokens and making a prediction, taking that prediction and maybe processing it again and spitting out more tokens. And then that prediction or those tokens are then decoded and actually sent back to you as a response that's readable. So just like any memory-intensive software program, large language models bring performance trade-offs, infrastructure constraints, and of course they cost money to run. And so in a bit more detail, why exactly is it hard to serve LLMs? Well, first of all, as we all know, they can be huge. Just as an example, hosting the 70 billion parameter version of the Llama 3 model can use around 150 gigabytes of GPU memory. Relative to that, OpenAI's GPT-4, rumored, estimated to have over 1.5 trillion parameters. And while the number of parameters is sort of just like a rough ballpark in terms of how big a model actually is or how intense it is to actually run, right, its memory footprint, I'm just trying to paint the picture that hosting these models, especially these type of models at this scale, requires having the hardware, the memory, and the infrastructure that can actually run them. And most of us, especially beginners, who are just trying to wrap their head around LLMs, just don't have that sitting on their desk at home. So not only can they be huge, but LLMs can be complex as well. An LLM is not just some function that, like I mentioned before, it's just spitting out text. There's a lot going on under the hood. The model is doing a lot of work in order to generate each token in its response. And one of the first things it's doing is tokenization. Tokenization is the process of breaking down text into smaller units called tokens, and these tokens can be words, parts of words, characters, like this hypothetical flowchart's showing. And only after tokenizing can the model actually process its input, do its magic, generate responses as new tokens, and then of course decode those tokens back into text that you can actually read. Then tokenization leads us to another factor. How much input can the model actually process at once? And this is what we kind of refer to as context length. Some models can handle hundreds of thousands of tokens, others can only handle a few thousand, but regardless of what that max is, this means that the longer the prompt, the longer the conversation gets, and the more compute the model actually has to do. But why does it make it slower? Well, that's because of the way that models actually generate responses. LLMs are autoregressive. Basically, LLMs generate a single token at a time. And each time a new token is produced, it's added back into the input, and that whole sequence is processed yet again to predict another token. And this loop repeats until that full response is generated. So think about that every time you're trying to make it, write your blog post or an essay, or one of your kids is trying to use it for an essay. It's doing that many times over and over again. And the longer the output, the more compute is required, of course, because each new token increases the amount of work needed in order to predict the next one. And here's just a simple illustration of what that autoregressive generation just looks like. Input the dog, the model might predict the next word as is, and then the new input becomes the dog is in order to predict the next word, barking, and so on, until the model predicts a special end of sequence token that tells it to stop doing this. So now we know that LLMs are not just big, but they're complex too, and now just imagine multiplying that by all of the users sending requests all at once at the same time. That's where scaling comes in and introduces a whole new set of challenges. For example, when demand spikes, you need to make more resources available quickly, and like any service, you need to dynamically scale without dropping requests. Then, somewhat unique to LLMs is this idea of it being stateful. You can't just send any incoming requests to just any available server and replica, because if maybe I'm chatting with the model, there might be session context that I need preserved. Otherwise, my conversation with that model might lose its continuity, and that makes this idea of load balancing even more complicated. On top of that, spinning up a new model can take minutes. So again, just another thing that we have to account for when scaling in order to meet demand. So I'm kind of rushing through it, but to wrap up this section, why is serving LLMs hard? Well, they're huge, they consume a lot of resources, and scaling them efficiently is even more complicated in their case. And so, again, for beginners and people who want to just kind of get into this space and understand why there are so many tools and what they do, my hope is that with an appreciation of more of the context behind the challenges, then you better understand what those models are actually trying to do and where they fit in order to try to solve one of those problems. And so, now we'll introduce the projects, starting with vLLM, which focuses on making the inference part of everything faster. So, vLLM is an open source inference and serving engine. It was born out of UC Berkeley by a group of researchers there. And simply put, its main goal is to speed up LLM output by optimizing how resources like GPU and so on are used. It's also a great example of a active, healthy, vibrant open source community. It has over 1,000 plus unique contributors the last I checked, and this just kind of speaks to the pace that it moves at in terms of features and improvements and so on. So how does vLLM actually achieve those things? So I'll quickly touch on 3 of the key techniques that vLLM uses under the hood. The first of which is called paged attention. One of the biggest memory bottlenecks in LLM inference is something called the KV cache. If you're not familiar with that, it's basically where the model stores the relationships between words that it's already seen, so it doesn't have to recompute them every single time. Right? So if maybe I told a model, what is the capital city of some city, then it would do all those calculations, save that information in this KV cache, and then the next time that I ask it, what is the capital city of another country, it will have already seen that what is the capital city part of that prompt, and be able to just pull out that value as opposed to going through its computation and figuring it out again. So that's the KV cache and why it's very important. So the vLLM team actually discovered that traditional systems were wasting between 60 to 80% of memory the way that they were managing this cache. And so, inspired by the way OS operating systems use virtual memory and paging, they applied the same technique, and instead of treating that KV cache as one contiguous block, they break it down into smaller chunks, pages, and that just allows for faster lookup, better memory management, and they actually reduced that 60 to 80% number down to just 4%. And this is all explained in more detail in the vLLM research paper if you want to look that up as well. Another key technique used in vLLM is called continuous batching, where traditionally in static batching, you can think of collecting a batch of requests that are coming in, processing them all at once, waiting for that batch to finish, and then beginning to work on the next batch of requests that were kind of waiting around. In dynamic batching, in continuous batching, instead of treating it like a static batch, you treat it more dynamically. So instead of waiting for this one batch that you're working on to finish entirely before starting on the next one, you're filling in that batch with new requests as they come in, as space becomes available. And this is especially ideal in high-load scenarios, and it just means that your GPU resources aren't waiting around idle, waiting for this current batch to finish because it wants to get started on the next one, but instead more dynamically used, so GPU resources are constantly being used. And yet another piece of the puzzle that helps with features like PagedAttention is its optimized CUDA kernels. If you're not familiar, CUDA is that low-level programming language that used to talk directly to GPUs, and vLLM comes kind of shipped with its own custom CUDA code, specifically optimized for those KV cache operations I alluded to before. And of course, this just helps with efficiency and using GPU resources better, which means cheaper, more effective, and so on. So those are some of the ways that vLLM makes a model run faster. But when you're dealing with many users or you want to serve multiple models, you need a system that can actually scale up, that can route the traffic, and actually manage all of the models that you're trying to serve. And that's where a project like KServe comes in. So KServe is that open source platform built entirely on Kubernetes, and it handles things like deploying, scaling, managing models in production. And it's basically a one-stop shop, abstracting away all of the, I guess, tough model serving infrastructure things you have to do. And because it's Kubernetes native, it's kind of built in with things like the fault tolerance and auto healing that Kubernetes is known for. KServe is also not just for generative AI, it's also for what they refer to as predictive AI, things like TensorFlow, PyTorch models as well, so more classic models. But how does KServe actually specifically help? Well, as I mentioned before, KServe manages autoscaling, which is crucial for production. And autoscaling is the idea of automatically creating replicas of models in order to manage the load as traffic increases. And the opposite, when traffic drops and you no longer need all those replicas of the model served, then it would scale those down and you can save resources. But if you remember, I mentioned earlier that LLMs can take minutes to load sometimes. So how does autoscaling handle that delay? Well, KServe also supports something called the local model cache. And this means that once a model is downloaded to a node, it actually is stored locally and kept in a sort of warmed up state where it's not using full resources. But this means that when traffic spikes and a replica of the model is needed, it can be loaded closer to instant and saves time on that startup. And finally, I mentioned the KV cache before. KServe also supports the KV cache offloading through a project called LM-Cache, which helps with things like larger context lengths, like those longer conversations I mentioned, where the KV cache can grow exceptionally long, and this allows for that KV cache to be offloaded to some other piece of hardware, whether it's memory or something else, and this opens up GPU resources to continue to work on the kind of computations at hand. So, we've covered some of the main pain points around inferencing and serving large language models. And now you know a bit about how vLLM makes models run faster, how KServe helps with the scaling of it on the operational side. And again, circling back to kind of what I mentioned and what I made this talk with the idea of, is that lots of people, beginners who want to learn more about this space, don't exactly have the hardware that's needed to see them in action, right? Especially tools like this, which is just meant for production. So unless you work for an enterprise company that has those things and you're hands-on, you know, doing your day-to-day job, that's the only way you can really learn about it. And so to help with that, I kind of Frankensteined, I guess, a demo that most people would be able to run locally on their laptop in order to just get hands-on experience with KServe and vLLM in some simple way. And so this is what that simple demo consists of. And at the very end, I also have I'll mention I have a link to like an article tutorial that I also wrote that's online. And so if you ever actually wanted to try this out on your own, you can. And that'll be at the end. But yeah, this demo consists of running a small, lightweight model. Obviously, it has to be if I'm running it on right on my laptop CPU. Using kind Kubernetes in Docker, which creates the local Kubernetes cluster. Once I have that kind set up, I guess you just follow KServe's quick start tutorial. Again, I tried to make it as simple as possible where it's just kind of copy and paste stuff in order to get things working. And KServe's quick start setup on the cluster works just fine. And then under the hood, when I do actually serve a model on this cluster that I've set up locally, I would be able to, I'm running vLLM, and vLLM is actually the one that's running my model. So here I just show what deploying a model actually looks like in KServe. Once you actually have a KServe cluster or a Kubernetes cluster set up and KServe installed on it, you use this custom resource, which is called an inference service. And basically, an inference service kind of equals a model in KServe land, because it's the main interface that KServe uses to manage the models and expose like an endpoint for serving the inference requests to that model. So here you can see I specified a model format or a model type, which indicates what kind of model I want to serve. I mentioned before, KServe doesn't just do generative AI, they do predictive AI as well. So this could have been PyTorch, scikit-learn, whatever type of model I want to serve. And then some of those runtime arguments are, of course, pointing to the Hugging Face model that I tried. I was able to run up to the 1 billion parameter version of Llama 3.2. There are much smaller models out there that are probably better for most people's CPU and heat source, I guess, so their table doesn't melt, but I got this 1 billion parameter one working. And at the bottom there is the server image. This is the Hugging Face server. It's KServe's runtime image for text generation models. Bundles everything you need in order to serve a model out of the box, basically. And then, you know, not shown below there is resource request limits, trying to limit the things. So again, you don't melt your table trying to run these on your laptop. So, well, let's see. I can show very quickly. I don't really plan to show the video, but I can kind of at least step through what some of this looks like. But basically at the top, the first line is just me applying that inference service. And this is, again, all local. So I've already set up my Kubernetes cluster. I've installed KServe, and everything's ready to go. And so here we have a pod deployed, which is able to host, or is basically setting up a vLLM server to deploy models. And again, I'm thinking of the beginner who has no resources to actually run any of these things. And so what happens here, you know, nothing in this output is specifically interesting for this talk, but it is at least somebody's experiencing, I guess, what vLLM logs look like out and like from the get-go here, and seeing, you know, what kind of parameters they would be able to run, right? Would they want to try maybe static batching versus continuous on their laptop, and seeing and being able to compare, I guess, the kind of output that you would get in an actual production environment using something like vLLM. And so that's just the KServe pod setting up, and it's ready to serve inference request. So this model has been loaded up now. And on this other side, on the top right, I'm just port forwarding. So now I can actually send requests to the model straight from my laptop. So nothing too special there. And then in the bottom left here, I'm just running a bash script, which is simply a curl request. And I have some kind of prompt in there. I have the name of my model, and I'm just running the curl request here. And on the top left, I'm following what the pod is saying, or what it's spitting out, I guess. It's logs. So the pod, which is where the model's actually being hosted. And so what we see here is, it's a little blurred out, I'm sorry, but apples, bananas, oranges was my prompt. But again, for somebody who is just on their laptop, they now have a Kubernetes cluster, they have KServe deployed and installed, they're hosting now a model, and now they're sending a request to it. You know, this isn't their AI assistant, but at the very least, it's their way of experiencing what vLLM looks like and what KServe can do. You see things like sampling params, and then there are so many different vectors I feel like a person can go into this space and decide to learn about, right? Maybe they play with the temperature of this prompt or the repetition, and they learn what those terms even mean in the first place, and so on. And then you could see that, again, unimpressive numbers because it's a small model on my laptop and it's a single request, but somebody would be able to watch it actually getting worked through here. And this might look different between using continuous batching, as I mentioned before, or static batching as well. And then ultimately, you do get your output and your response, if I'm not getting cut off, because it is 2:36. But I don't know what happened. Okay. Even if I record a demo, I still get somehow cursed. So there is just the response, right? So somebody can look through and be like, okay, I have my model. The response was okay for a 1 billion parameter model. It says grapes and more. If you remember, I sent it some fruits. And yeah, completion token. So the prompt token was tokenized as 8 tokens total. The completion tokens, meaning this part, grapes and more, counted as 5 tokens. So anyways, there's like a lot of little things that I think somebody can experience if they want to just run the thing and see what it looks like and be able to play around in a little bit of a sandbox. And that's the idea. So I will go back to just the very end here, because that is the end. So that's the demo, that's the talk, and here I just have some links. There are the Slack channels for both projects if you do want to get involved. Both projects have open office hours every single week, and KServe is under the larger umbrella of Kubeflow, so you would be joining that Slack as well. But yeah, very open, lots of issues, lots of PRs to review, lots of everything if you do want to get involved. On the bottom right is just that link to an article, as I mentioned before, and in case you want to contact me, that's there too. But yeah, thank you for listening. And I'll stick around if you have any questions.